Thank you for being here, attending this talk. So today I'll talk about noise-assisted digital quantum simulation of open systems. So this work was developed at Institute of Theoretical Physics and Center of Quantum Bioscience at Ulm University, Germany, in collaboration with University of Minho and the International Iberian Nanotechnology Laboratory in Portugal. So let me give you a brief overview of this work. So here we propose a quantum algorithm to simulate Markovian dynamics of open systems in NISQ devices. So more specifically, we aim at simulating this Lindblad equation. So we have some Hamiltonian of our choice. And then we have that the noisy dynamics are generated by this Lindblad dissipator, which is of the form of stochastic noise. Okay, so throughout this presentation, I will refer to the implementation of this Lindblad equation by your technique, but I remark that we can also implement other noise channels of our choice as well. So this type of Lindblad equation is usually hard to simulate in current quantum devices because standard approaches require full error mitigation or fault-tolerant quantum computer. So here, instead, we try to use the intrinsic noise of NISQ devices as a resource for this particular quantum computation. So we use this noise of the NISQ device to emulate the actual noise of the system, of the open system we want to simulate. So we do this by using a set of noise characterization techniques and error mitigation techniques. And we find that we can have potential exponential reduction of computational resources relatively to these standard approaches that require full error mitigation. These are some of the references that have been proposed. So in a quantum computer, we can use several types of techniques to evolve a quantum system. In this work, we use a Trotter-Suzuki product formula. So let's imagine we have a noiseless quantum computer. So we apply some evolution operator to initial state to evolve it up to time t. And what we do is to decompose this evolution operator into a kth order Trotter-Suzuki product formula. So it's something like this. So we apply this U operator, which is just a Trotter layer, okay, of kth order, sequentially for d times, okay, so for d Trotter iterations. So a first order product formula is shown here. This is just a usual form, well known, where we decompose Hamiltonian, as usual, as a sum of terms, where each term is given by a Pauli string times some real coefficient alpha j. Now, in a noiseless quantum computer, the output state is a pure state, right? So, but right now, we have at our disposal noisy quantum computer. So if we implement this Trotter-Suzuki product formula, what we'll have is some noisy dynamics, okay, of the quantum system. And this is because these Trotter layers are noisy, so they can be decomposed in native quantum gates, and the implementation of these gates is, as we know, faulty for now. And this evolution of the open system can be traced by this Lindbladian. So here we have an Hamiltonian, which is Hamiltonian we encode in the Trotter-Suzuki product formula, plus some Lindblad dissipator, given by the intrinsic noise contribution of the quantum device. So if we want to use the intrinsic noise of the quantum computer in order to emulate the noise of the system we want to study, then we need to know to characterize this noise that acts on the qubits and somehow manipulate it. And for that, we implemented a set of techniques to benchmark the noise. So we use this type of randomized benchmarking technique called cycle benchmarking. And then we reconstruct the error such that the output of this procedure is a capital K qubit stochastic polychannel. So it's something like this, where epsilon k is the error probability, often associated dissipative Pauli interaction pk. So this Pauli string pk acts on k nearest neighbor qubits. Okay. So here on the right side of the slide, we have an image illustrating this. So we have the orange circles that are the qubits where we encode the open quantum system degrees of freedom. And then we apply the Trotter-Suzuki product formula. So we just repeat the Trotter layer for d times, so for the Trotter iterations. And then we characterize the noise over one Trotter layer, okay, because the others are essentially the same as the first. So to give you an example of a k-qubit stochastic polychannel, so for k equals 1, we have the single qubit stochastic channel applied to the qubit m, it goes like this. And for k equals 2, for 2-qubit stochastic channel, we have a sum of the single qubit stochastic polychannels acting on qubits m and m plus 1, and some correlated noise acting on both qubits. So we found by doing several experiments on IBM quantum computers that it's enough to characterize a 2-qubit stochastic polychannel in the quantum circuit, and this provides an accurate description of the noise on the trotter layer. Okay? So in general, we believe this will be satisfied for local Hamiltonians. So knowing the form of noise that we have in the circuit, then we can expect that if we proceed to the actual time evolution in the quantum circuit, that the dynamics of these of the qubits of the open quantum system will be given by this Lindblad, and where we have again the Hamiltonian that's encoded with a product formula, and this Lindblad dissipator, which is of stochastic form, where gamma k here are the decoherence rates given by the characterized error probability, okay, of the stochastic channel k over delta t, which is the trotter time step. So you may be wondering why, if I assume that the noise is given by a stochastic channel, and of course we can have coherent noise acting on the qubits, etc. So both in the noise characterization and in the time evolution, we applied randomized compiling, which is essentially a quantum error mitigation technique that transforms coherent noise into stochastic one. So let me give you an example in order to try to convince you that this is the case, that this is a faithful characterization of the noise. So we implemented this molecular energy transfer model. It's given by this Hamiltonian in an array of qubits in the IBM quantum devices. And this Hamiltonian is very useful in transport problems in biology, such as studying quantum effects in the energy transport in photosynthetic systems. For instance, here we have the light harvesting complex of purple bacteria, where we have 2 rings, and each ring is composed by several molecules. So an exciton, so one of these light harvesting molecules absorbs a photon, creates an exciton, and then this exciton is transported across the molecules. So here the aim is to try to understand if quantum effects enhance or decrease the efficiency of photosynthesis. And in general, against noise, because these are room temperature biological systems, so the magnitude of noise is quite high. So classical computers usually face some difficulties to simulate these systems, mainly due to the large number of molecules that exist in these pigment protein complexes. So going back to the quantum simulation, we did some proof of concept simulations with 2 and 4 qubits with these trotter layer structures. And these are some of the results we obtained. So we implemented noise characterization in IBM quantum computer, and then the time evolution simulation. So we can see here we measured the population terms of a density matrix, and we can see that the dots are the quantum simulation results, and the crosses are a classically solved Lindblad equation where the error rates, so the decoherence rates, are the ones that we obtain by the noise characterization. So we performed this Lindblad equation by trotterizing the superoperator that generates this noisy dynamics, such that we remove the bias of a trotter decomposition error when comparing with the quantum simulation results. So these results tells us that we have a reasonably accurate description of noise with these 2-qubit stochastic channels, both in the 2 and 4-qubit simulations. So the next step is how can we control the noise in the quantum circuit? So we start by having some initial decoherence rates, which are given by this gamma k, defined by the characterized error probabilities over delta t, and we want to simulate some target decoherence rates, so some target Lindblad equation, okay? So we do this adjustment of the decoherence rate in 2 steps. So if we want to increase gamma k, then we decrease delta t. Okay, we decrease the trotter time step. And in this way, we increase all the decoherence rates of all the stochastic channels. Okay? And then we can selectively, in the second step, reduce the error probability of each stochastic channel k by this factor here, 1 minus rk. So rk is what we call a mitigation factor. that goes from 0 to 1, and it's essentially the percentage of the noise that we want to mitigate. So 0, it means no mitigation at all. 1 means full mitigation of this particular stochastic channel. So more specifically, we do this in this way. So here we have a plot, so vertical axis, the coherence rates, which are associated to the polynoise channels K. And we start by these orange triangles, which are the initial decoherence rates. Now, in the first step, we decrease delta t, such that, again, we increase all the decoherence rates. And such that the resulting decoherence rates are equal or greater than the target ones. And the target ones are given here by these blue squares. Okay? So in the second step, we use a partial noise mitigation technique that allows us to selectively reduce the error probability of each polychannel, such that in the end, we have some target decoherence rates given by this formula over here. Okay, so let me give you, first, let me explain to you this partial noise mitigation, which is we use the conventional probabilistic cancellation, but we, instead of fully mitigating the noise, we partially mitigate it. Okay, so very succinctly, we have some characterized noise channel, which is given by the stochastic channel, and we partially invert it, such that this partial inverted channel, we apply it to each trotter iteration, such that we cancel part of the noise. And this partially inverted channel is given by this, defined by these error probabilities epsilon prime k, okay, which denote the magnitude of noise that we want to mitigate for this particular stochastic channel k. So generally, it works like this. We have the trotter layer, and we generate several copies of the circuit, and we sample. So we apply these Pauli operators probabilistically to each trotter layer and to each pair of nearest neighbor qubits, because we characterize 2-qubit stochastic channels, and we therefore have to mitigate these ones. Okay. So, and in the end, so we sample these, we generate the copies, we sample, we apply these Pauli operators, and in the end, we do some classical post-processing of the results, such as the usual probabilistic error cancellation. So let me give you an example of this. So again, we implemented this molecular energy transfer model for a 4-qubit simulation in emulated IBM Q devices, which means essentially that the noise is classically simulated by Qiskit. And we mitigated the interactions, so these dephasing interactions, so for single qubit and correlated 2-qubit dephasing noise. For 80%, okay, so we mitigate 80% of these dissipative Pauli interactions in the circuit, and all others by 10%. This is just a mere example. And then we do the quantum simulation, this emulated IBM Q device. We measure the population terms of the reduced density matrix, and we compare it to the classically solved Lindblad equation, where the decoherence rates are given by these mitigated interactions. Okay? And we can see that the results agree reasonably well. So now let me briefly mention some limitations of the method, and also some advantages. And for that, I need to introduce this total mitigation cost. Okay? So this total mitigation cost is essentially given by a product over all trotter iterations T and all pairs of nearest neighbor qubits of C. So this C is defined by the total magnitude of noise that we want to mitigate in the trotter layer. So the sum of all epsilon prime k. Okay? And so if we implement the raw simulation without any error mitigation techniques, we have that the variance of a measured observable scales inversely with the number of shots employed, right? So when we implement this probabilistic error cancellation, or this partial probabilistic error cancellation, we have this multiplicative factor of C total square. Okay, so this means that if we want to reach the same variance as a raw simulation with this mitigated simulation, we have to implement C total square more shots. Okay. So we can analytically calculate how this C total square scales with some simulation parameters. And for this trotter type circuit, And we have that the scaling is exponential in lambda, which is a parameter that is found by experiments, okay, usually small. N, which is the number of qubits in our quantum simulation. D, which is the number of total iterations. And epsilon R, which is, again, the total magnitude of error that we want to mitigate in the circuit. Okay. So these results should be put in contrast with full error mitigation, where C total square scales with epsilon, which means that R here is always equal to 1. But if we employ a partial probabilistic error cancellation, we can have RK less than 1. Okay? So let me illustrate this aspect a bit better. So we performed some noise benchmarking experiments in the IBM quantum devices, and we calculated the total mitigation cost with these characterized error probabilities. So here plotted is a total mitigation cost as a function of number of total iterations D, and as expected, we have an exponential increase of this cost with the number of iterations. But for different R, we have different scalings of this cost. And we can find that as we reduce R, we exponentially reduce C total, okay? Which means that we need to execute for a smaller R exponentially less circuits in the quantum device, or employ exponentially less shots in the quantum device. And this allows us to choose a smaller R to have to simulate the quantum system for longer timescales, as here shows. So, which means we can employ a higher number of total iterations D for the same circuit budget. And this exponential decrease of quantum circuits that we can have for a particular open quantum system model is what we mean by having a potential exponential reduction of these computation resources in the form of a classical overhead, which means in the form of the number of executed circuits, relatively to standard approaches that require full error mitigation. So, which means that R equals 1. Okay? But in this case, by using the noise as a resource, we can employ partial probabilistic error cancellation, because the noise is helping us to simulate the target Lindblad model, which allows us to have a reduced mitigation factor, and then execute more circuit, simulate the system for a longer time scale. So, do I still have time? How much am I? Yeah. So, let me talk about this resource estimation that we did for this technique. So let's say we have a quantum device that for a given period of time we can execute max circuits, okay? And we want to simulate a target open system model given by these decoherence rates on a NISQ computer, okay? So in order to find if we can simulate this specific open system in this quantum device, then we have to have that the total mitigation cost square must be equal, I mean similar or smaller than the total number of circuits that we can execute for a period of time in this quantum device. So we can kind of manipulate this equation such that we reach this inequality, where we have that the maximum allowed total error probability in a total layer must be similar or less than this right-hand side of the equation. So what we have here is, so this uppercase gamma is just a sum of all the target decoherence rates. And this means that the smaller is this gamma, the harder will be for the quantum computer to simulate this system, okay? But we can, even if we have a smaller total gamma, okay, this uppercase gamma, we can still increase the capability of the quantum computer to simulate this target open system model by exponentially increasing the circuit budget, so the total number of circuits that can be executed for a period of time. So this is some resource estimation of this technique. And to conclude, so we believe that some interesting applications for this technique is, of course, NISQ computers, but also quantum analog simulations. And regarding the latter, we think it's interesting because the quantum hardware does not need to be changed in order to tune the decoherence rates, in order to simulate the target Lindblad model. And this is done in a purely digital fashion, resorting to noise characterization and error mitigation techniques. So the third point is that we believe that the most efficient types of noise to be simulated with this technique will be stochastic polynoise channels with medium or large decoherence rates. However, I remark again that this technique is not restricted only to stochastic polychannels. For example, in this preprint we published about this work, we also talked about how to implement amplitude damping in addition to this stochastic polychannel. And finally, this is our ongoing work. We are trying to generalize this technique to simulate non-perturbative dynamics of open quantum systems. So if you're interested, I'll be happy to discuss with you. And yeah, thank you for your attention, and these are the collaborators of this work.
Thank you for the very interesting talk. Just to understand a bit better how you would choose R in a given experiment, are you basically looking to kind of pick the largest R that gives you that kind of the time you're willing to get away with? Are there any other factors that would influence your choice of R?
Yeah, so we start by these initial decoherence rates, okay? So it depends on the characterizer probabilities of the quantum computer. And we start by having an initial delta t, okay, arbitrary delta t. And then here in the first step, we decrease this delta t such that the resulting decoherence rates are equal or greater than the target ones. And then this Rk will depend on the magnitude of noise that we need to mitigate for each particular stochastic channel. Okay, so it depends on the particular decoherence rates and on the characterized error probabilities of the quantum device in general.
Thank you.
Hi, thanks for a good talk. My question is about the error characterization side. So randomized compiling and even more so cycle benchmarking, were typically designed to work with Clifford layers of operations. So is there something going beyond that that's lurking behind what you're doing? Because my understanding is that you're applying that to Trotter steps, so non-Clifford operations.
Yes, that's an interesting question. So we changed a little bit the quantum circuit, so the Trotter layer, such that we remove all single qubit terms of the Hamiltonian, because, well, 2 qubit gates are usually 2 orders of magnitude noisier, so removing the single qubit gates we expect to not have a very high influence on this noise characterization. And then we change, so when we decompose these 2 qubit terms, 2 qubit poly terms exponentiated, okay, we have some Z rotation gates, right? And we change these Z rotations to Z Pauli operators, such that in the end, we keep the 2-gate structure of the Trotter layer, but we have that for every even application of Trotter layer, we have the identity. So essentially, the Trotter layer turns, this transformed Trotter layer becomes a Clifford circuit.
All right, let's thank the speaker again. And have the next speaker come up.